Today I want to explain what is the simplex algorithm and how it works, showing also a basic implementation in Python. Let's start with a problem. You are a company that produces two types of paints, A and W, on separate lines with daily capacities of 60 and 50 liters. Producing 1 liter of A requires 1 hour of labor, while 1 liter of W requires 2 hours of labor, and they make respectively $20 and $30 of profits. If we have a limit of 120 hours per day, how can we maximize the profit? We can describe the problem with two variables, A and W, and impose the conditions. Then we can say that we want to maximize the hours of work per day, so we put A plus 2W equal to 120. With simple algebraic operations, we can see that under these conditions, maximizing the profit is equivalent to minimizing the W. To minimize the W, we simply set A to its maximum, 60, and derive W from the equation above, obtaining W equal to 30. In this scenario, the total profit is $2,100. But how do we know that this is the real optimal solution? To get the true solution, we can use the leapfrog method from SciPy. We can see our cost function written as C, an array, and its signs are inverted because our method, the leapfrog function, searches for the minimum, not the maximum. So we will have to invert the result again in the end. Then we can see our equations as our limits written in this format, and the bounds telling that A and W must be greater or equal than 0. And then we can just run the leapfrog method. What we want to understand in this video is how this leapfrog method works. And this is the interesting part. If we run the program, we can see that the solution is our actual solution. So the A is 60, W is 30, and our total profit is 2100. So our result was correct. The first step of the simplex algorithm is turning our inequalities into equalities using the so-called slack variables that will change their values to force the inequalities to become equalities with their limits. Now we get the key idea of the simplex algorithm. Since the cost function is linear, we know that the optimal solution is on an edge of the polytope representing the feasible solution of our system. In this case, we have a polytope in a 5-dimensional space where each direction is representing A, W, S1, S2, and S3. To get an edge of our n-dimensional polytope, we have to turn to 0 enough variables to transform our system from undetermined to determined, and calculating the coefficients for the variables that are not 0, we get the edge of the polytope. Looking at our system, we can do this operation by selecting 3 columns from our new matrix and then solve our linear system. In general, we have to select a number of columns equivalent to the number of equations we have in our conditions. Now we have all the informations to look at the Python implementation. In this version, we search the maximum, so we don't have to flip the cost array C, and we can leave it as it is. The first step is to get our H matrix that we will use to select the column. The slack variables are represented into this mp.i, and we will have to search for all the combinations of columns to calculate the score on each of them, and then see what is the maximum. We can see that the combinations are computed by the combinations function from itertools, and we can select our columns into the matrix M with this line of code. Then we simply solve with a NumPy function our system and find our solution X. If we encounter an impossible solution, we just skip it since it's a non-feasible solution and we don't want it. And now we have to create our solution array. First, we create a zero vector, so a vector containing only zeros, and then we insert the value of the solution in its corresponding position in the base vector using the indexes, and then cut out the slack variables with this last line of code. Now we have to check if all the variables are greater than zero, because we can't have negative values of a, for example, because we can't produce negative paint. It doesn't make sense. And we can't have negative slack variables because this would mean that, for example, a would exceed its limit of production, and this is not a feasible solution. So if we respect all these conditions, we can calculate the score of our X effective, which is our final solution, and then append it with its score to the solutions list. We will just search for the maximum of calculating it with respect from the first element of this list append contained in solutions, and then we return it, and we have our solution. If we now run our algorithm, we can see that we get the same solution of the one that SciPy gave us. So it means that it's correct. In fact, we can see max profit 2100, optimal A and W 60 and 30. Looking at this implementation, you will probably wonder, is there any faster way to get this result? Because at the moment we are searching for all the edges in the polytop, and this is not very efficient because we have to check lots of cases. And what we can do is navigate through the edges of the polytop in searching the maximum. And what we can do is start from an edge 0 and then check the neighbors, his neighbors, so the edges that are near to him that are connecting in this polytop, and check the result. Then we take their maximum and start again to repeat this process from that point. In this way, we get to this optimal solution in a very faster way because we don't have to check all the edges, but just a small fraction the route that connects our starting edge to the optimal one. This method is implemented in this code because we can see that it practically does the same. It does it it poses a condition if we found the max, and we have to a while if we don't have the maximum at the moment, we keep repeating this iterating process. And the center of this part is this one. We create our new neighbors each time for each edge. And for example, we can see, this is an example, the tuple from of the columns. So every edge is practically a selection of the columns. We can get a neighbor from our current edge if we change just one column from the selection. So for example, in this case, we have 0 and 1 that remain constant, and the 3 that become 4. In this way, we just search for the neighbors, repeat all the steps before, and we return our optimal score and our vector corresponding to it. We can test it in this script that I built with the Claude, and we can see if we run the terminal that the time of of calculating each solution with this different algorithm is very different. We will see that okay, Limprog is the faster in above all the three because it's 0.001 seconds. V3 is in the middle because it's 0.048, and V1 it's the slowest, it's 0.28 seconds. So we have a difference of 2 orders in the time of computation. So we can see that if we increase the dimension of the matrix, now is 12 by 6 the dimension of the matrix A, we can see that the V1 version, the first we built, is scales very in a bad way with respect to V3 and Limprog. I'm currently running the V1, this test script with a great num with an high value of h and w. So I insert h8, which is the number of equations, and w equal to 20, which is the number of variables. And we can see that it doesn't even execute. It's so slow that it doesn't work. So we can just try with smaller parameters. So we can set 15 and keep 8. And probably it is still blocked. Okay, it's blocked. I can, if we now, okay, now it's working. Wait, okay. We can see that it's very, very slow. Now I will stop and continue after it finished. Okay, now it finished to run, and we can see that the time difference is absurd. It's 7.5 seconds compared with 0.09 seconds and 0.01 from the Limprog. So our implementation, our optimized implementation is very better um, compared with the one that is not optimized. And we can see that this is fundamental if we want to have a real application where the dimension of the matrices is very big. We have different, we have very difficult system to compute, and we can't do calculations, useless calculations like in V1. Of course, the leapfrog method is always is unbeatable. It's practically better in by a 10x over the V3, but this is normal. They probably implemented some optimizations, some mathematical optimizations that obviously I didn't know, and but we is not that bad with respect to the leapfrog, the V3. So this was it. I hope you liked the video.